gives us the model which it thinks is the best model. So for now we'll keep it enter. Let's see what do we have in statistics. Yes, we want to see the model fit. R-square change, or what is the R-square change? R-square change is something, so for example, let's say that it develops a different, like for example in stepwise regression, it develops one model with few very independent variables, and then it develops another model with few more independent variables. Then it gives you, in that case, it gives you how the R-square value is changing. In that case, we usually use R-square value. In descriptives, it gives you the mean, median, mode, etc., all that. Part and partial correlations, it gives you all these values that we just did using the correlation analysis. And then let's do the collinearity diagnostic, which is the multicollinearity diagnostic. And then the confidence intervals, by default it's 95%, so let's keep 95%. We continue. Plots. Now SPSS also gives you the plots. What do we want to plot? Let's see, we want to remember that to check the assumption that the errors have constant variance, we plot the normalized predicted on X and we plot the normalized residuals on Y. So let's do this one plot so that we know whether our assumption is satisfied or not. Let's do another plot in which we want to see how our observed value in the field, which is the dependent variable, which are the ones that we observed in the field, or the data, that the actual data, how it is related with the predicted. It should be a diagonally straight line at 45 degrees, or something close to it. If our model is a good model and it's explaining, or it's giving us the values close to what we observed in the field. Okay, and then we do the normal probability plot, which is the QQ plot, to see whether our assumption that all the errors are distributed normally is satisfied or not. Let's continue here. Let's see what is in the options. We already used this, and let's do okay. So see, it has included all the variables that we selected in our model. This is important, which is the model summary. It's giving you a value of R, and it's giving us a value of R squared, which is the coefficient of determination, which is 0.72 here, which means the model that it has given us is a strong model. It has a R square value which is close to 1, so which means this model is a good model. It is just what we see from here. However, it's possible that some of our variables are not at all contributing anything into the model. So we'll see it shortly. Adjusted R square, these are the different values, so we are not discussing it. So significance 0 means here that the model is significant. If this value, significance value, is greater than 0.05, which means the model that we have, which we have here, is not significant, or it's not good model, it's not a strong model. Although the independent variables have no significance value in our model. And then let's come here. It gives this B values. Now let's interpret these B values. These are the beta values. Okay, I will use that. Okay, I'll use it. Let me finish this first, and let's pay attention to this first now, and then we'll use your file and we'll see how does it work. So these beta values are the regression coefficients. And how do we interpret that? See, this is a constant, and this is 0.545, which is the posted speed limit. Lane width is negative, has a negative relationship, which means that it's showing that as the lane width is increasing, the posted speed is decreasing, which is, of course, is counterintuitive. Median width, excess density, and then the segment length. Let's see how do we interpret it, which means if I keep the lane width, the median width, the excess density, and the segment length, if I keep all these independent variables constant, if I make no changes in these variables, then by increasing the posted speed by 1 unit, so for example, if I have posted a speed limit of 40, and if I increase it to 41 miles per hour, then the change in the dependent variable will be 0.545. That is how we read a regression model. So for example, if I keep all other variables constant, if I keep the posted speed limit constant, lane width, all these 4 variables constant, and if I make a change, a unit change in segment length, if I decrease the segment length, let's say by 1 unit or by 1 mile. So let's say if my segment length is 2 miles, I find out the value of y, and then I make a unit change into it. I decrease it by 1. I change it to 1 mile. Then my speed or my dependent variable will be reduced by 8.37. Clear so far? How do we interpret these values? Everybody? Yes? Oh, okay. So these are unstandardized coefficient and these are the standardized coefficient. It's something which is which it normalizes. What we usually, thanks for pointing this out. What we usually do is we use these beta values here. Sorry, not these standardized, but these unstandardized coefficients here. You saw that like it computes the residuals, it does the normality, and then it gives us the standardized value. But it does not have any constant here. So what we use are these B values for our model. Okay? These are different statistics which are highly advanced. They are significant but not much significantly affect. Yes. Do you have any question? Okay, we are going there. These are the P values. See its significance here, which shows SIG. These are the P values. These are the T values computed, and these are the P values determined. So let's interpret these. P value of 0.0. This is, of course, less than 0.05, which means our hypothesis that the posted speed limit is not related with the speed is rejected, and we will keep this variable. 0.757, highly significantly greater than 0.05, which means our hypothesis, our alternative hypothesis, that lane width is not related in this case, in the data set that we have, lane width is not related with the posted speed limit, is accepted, which means it's not lane width is not playing any role in our model, so we will take that out. 0.034 median width, it is close to 0.05. We may or we may not keep it, it's up to us. So we can take it out, it's not going to affect our model much. Excess density is 0.005, which means in this model, it's explaining our null hypothesis is rejected, that excess density is not related with the speed limit, so we can still keep it. However, I would take it out. The reason being, see the sign here? Intuitively, this should have been negative, which means the way that I have collected the data, or the way that I have coded this information, there is some ambiguity or there is some problem here. So I won't keep it, because then the question may come, how come increasing the number of driveways will increase the speeds of the vehicles? So I would, in any way, even though it's significant here, I would take it out. Now in the segment length. The segment length is playing a role. It's showing that the segment length explains the variation in the speed. This is one. So this, we checked the significance of all of our variables. It did the interpretation of the beta values or the B values here. Now this is the multicollinearity test. Now you see here, all of these are less than 4. Though segment length is higher, and then the next higher is posted speed limit. And we also saw from our correlation analysis that the segment length and the posted speed limit were somehow were also correlated with each other. However, our VIF value shows that all of these are less than 4, which means that though it can create a little bit of multicollinearity, but it's not that high that it will significantly influence our model. So we can keep both segment length and the posterior speed limit in our model. All these VIF or variance inflation factors are less than 4, highly less than 10, which means there is our assumption that the independent variables are not correlated with each other, or there is no multicollinearity in our model is correct, is satisfied. Okay, and let's see this chart. Yes, this chart is, okay, this one first. This is the chart that tells us the if there's the QQ plot or the PP plot. Okay, there are two plots that we can do, QQ and the PP. Let's see which does it have Q? No, it does not have. So when we do the normality test, either we can have a QQ plot or we can have a normal PP plot. I really don't have I cannot tell you the difference because I am not sure what I mean, I know, but it's like it's quite vague. So let's not go in there, but either you can have a PP plot or you can have a QQ plot to see if all your errors are normally distributed or not. From here, we see that the errors are fairly normally distributed, though there is some deviation from normality here and here, but they are still close to this diagonal line which is at 45 degrees. So our second assumption that all errors are normally distributed is also met or satisfied. If the distribution was something like that is going way up here, then it's going way down here, and then way up here, then we would say that no, errors are not normally distributed. Then we need to go back and change our model again. Now here, this is our third assumption, which is that the error variance is constant. We plotted the predicted values versus the residuals, and we see that we are seeing a pattern here. See, all these points are merging. It's kind of it's scattered all here, all over here. These are merging here, which means there are some outliers, or there is there are few factors that are affecting the due to which the variance for the error is not constant, as we see as that all these points are merging here. So this might be because of some outliers in our data. However, most of them or majority of them are scattered normally. So our second, another assumption that the errors have a constant variance is also fairly satisfied. But if what we can do is we can take those outliers, make some changes in our model, and then make sure that all the errors have constant variance. And this plot is this is our observed values, and these are our predicted values. This, in case of a good linear model, this should follow a diagonal straight line or a 45-degree line. Let's see if it adds a line here. No, so it somehow. So when I develop a line or generate points using my prediction model, what it should have is it should follow this diagonal 45-degree line, and all these points are, since they are falling close to that line, which means the observed data is fairly is being explained by our model, or the estimated values that we have computed using our model is explaining what we observed in the field. So we can use this model to predict our other values or our future values, provided that our variables or the values that we take, they remain within the same threshold. If we change the thresholds of our values significantly from what we collected in the data or we collected in the field, then our model might not be that reliable. So let's see what else we can plot here. What else we can do is